Welcome everybody. Today I'm gonna talk about um, infinite dimensional Banach spaces, which has shadow base, and I will take this base and turn it to a kind of totally order, which is a kind of generalization of lexicographical order in finite dimensional R to the power of n spaces. Before giving our main results, let me give some definitions which is needed for our work. So let's say we have a vector space E, and it could be, of course, infinite dimensional. And let's say we have a subset of K in this E vector space. And if the subset of K is closed under the addition and it is positive homogeneous, and if we have a zero vector intersection with minus K, then this subset is called cone. So this is a kind of characterization of partial order in the vector spaces. So indeed, we have two ways to do that. So the first way, giving algebraically, and the second way is geometrically. So at the moment, I am using geometric way to give a partial order in a vector space. So in algebraic way, which is called spaces or partial vector spaces, so we can think that we have a vector addition and we have a scalar multiplication, and moreover, we have an order structure which is very friendly with this addition and multiplication, and you can give as a axiom of this vector space. But in this case, it is more geometric way. So we only start from a subset of vector space, and we put some conditions on it, these three conditions. And if we have these three conditions, then that means we have a cone. So it is not very hard to imagine why we call cone these objects. So if you think in a real numbers, or if you think actually in R2, the shape of this kind of object looks like a cone. And let me mention one more object, which is slightly more general than cones. And if we don't have this sharp corner properties, this object is called a wedge. When we are writing summation, of course, we mean Minkowski sum. If we add two sets each other, that means we are taking element of each set and summing together. Likewise for a scalar multiplication. So now I will tell you how we can get a partial order if we have a cone structure in that vector space. So as you see, it is in a straightforward way. So we will define a number is greater than or equal to other number if the difference of these two vectors is inside of the cone. So this relation satisfies a partial order relationship. And now here we go. We have a partial order in that vector space. So if we have two different vector spaces, and if we have two different cones in that vector spaces, we can kind of classify this kind of vector spaces by using order isomorphism. So what is order isomorphism? It is a bijection going from one vector space to the other one, and basically mapping the cone of the first space to the second one. And I also need to mention that lattice property, which is really important property, and which makes Banach ordered vector space to real spaces or ordered vector space to Banach lattices. So if we have supremum or infimum of each x and y in a vector space, then this property called lattice property. And if we have this property, then we have really good decomposition. Which kind of decomposition? For example, I can write each element of vector space as a supremum of x0 minus the supremum of minus x0. So I have a decomposition of x which can be written as a positive vectors differences, right? So actually we use a kind of different notation for that one as well. Anyway, so if we have additional this property for a cone, if the union of negative part of cone and union of positive of cone give us all vector space, then definitely we have a totally ordered cone. That means we can compare each element to each other, right? Very well. And let me remember what is called lexicographical order in a finite dimensional case. So actually this is this relationship. I mean, we call a vector which has n component here is less than the other vector when we have same relationship for each of these components. We can think this as a pointwise relationship. And of course, we are looking at pointwise relationship from left, from beginning. And when we got this relationship, we are convinced about that the one vector is greater than the other one. It's like a dictionary order. So let's say x1 is less than y1, then we are done. We are not looking x2 or y2. So x2 and y2 could have a different relationship. For example, x2 could be bigger than y2 in this case. Okay, so probably you know that the definition of Banach Schauder bases in a Banach spaces, and we need to use a norm for giving Schauder bases because we will give this definition by using a kind of convergency, and for a convergency, of course, we need a topology. Very well. So let's we have a Schauder base, which we will use Bn notation for that one. And if we have a Schauder base, that means each of vector in this vector space has this kind of representation, x equal alpha n times Bn. And moreover, we can construct this kind of subset of this vector space by using this projection. So for each k, we could define that set. So P1 will be the consisting of the vectors in E, which has positive first projection. So B2 is going to be a vector of subsets, which will be the first projection has to be 0, and the second projection could be greater than 0, must be greater than 0, and so on. So the Bn set will be consisting of vector x, which has this property. In other words, up to n, each of projection should be 0 for this vector, and nth projection should be greater than 0. And if we get together all these sets, then if we add 0 vector, then we have a cone structure in a Banach space. And as I mentioned before, if we have a cone structure, then we got totally ordered vector space. So I proved that things here by using the totally ordered vector lattice definition. So I show how it is closed under the addition, how it is positive homogeneous. Moreover, how we have a supreme of each pair of vectors, and we got a cone here. By using that cone, of course, we can classify Banach spaces. So let's say we have a two cone structure in a Banach space, and of course, these cones has obtained by using same shadow bases or equivalent shadow bases. Then we have ordered isomorphic vector lattices, which is really, really good property and makes our theory consistent. So we have a proof for this theorem. In the proof, I used closed graph theorem, and by using this proposition, we already have a corollary which say that, let's say we have two totally ordering cones in a Banach space by inducing different equivalent Schauder bases, then they are ordered isomorphic vector lattices as we expected. So by using this projection, we can also prove an ordered property, which is known as a maximal order ideal in EK structure. So order ideal is similar to ideal of fields. So the definition of ideal is if we have an order relationship, let's say we have a 0 is greater than x is greater than y, and y inside of the our order ideal candidate set, then x has to be as well in this set. So you can think that if we have a ray in real numbers, for example, and if the endpoint of this ray is belong to our order ideal candidate set, then all the elements of array, which is of course positive direction, starting from 0 or any positive number, should be belong to order ideal as well. And of course, we need to have a kind of subspace property in this order ideal. It's not only a set structure. And in this proposition, we show that this I1 should be maximal ideal. And the next proposition shows all IE, I mean all the composition union of this IB, IE2, IB3 is countable cardinality. This is also another good order properties of this order. And as we expected, if we have a quotient space, and this is going to be lattice isomorphic to R, which can be seen as this order is a kind of generalization of totally ordered ring in R. Moreover, we have an order convergency property. So if we have an order convergence sequence in a vector space, then it's any projection again converge to 0 vector, converge to 0. Of course, that is the real numbers convergence, because this is geovalued function, and this is also good property, and we can use this lemma in the next corollary. So we can also give an example. This lemma is not going opposite sides. So, for example, we have a norm convergency, and but in this case, we don't have order convergency, as you see. So we can think about this sequence in C0 space, and with supremum norm, of course. So it is easy to see that this sequence converges to 0 according to supremum norm, but it is not order converged because, as you see, this number is strictly greater than 0, but the infimum of xn, the sequence, is greater than the number. This is, of course, the disadvantage of our lexicographical order. And we have an example which implies order convergence and does not imply the norm convergence as well. If you look at standard case of C0 again, you will see that this is correct example for my claim. And since we have a Hamel base in every vector space, especially in finite dimension spaces, so this shadows bases, they are equivalent to Hamel bases in R to the n. So we have a totally ordering cone in R to the n, like proposition 3.2, as you see in the above. And we have one more corollary, actually. Every finite dimensional totally ordered vector lattice is order isomorphic to this finite dimensional. This is also a very good conclusion of our result. Moreover, we have, which is a kind of generalization of mentioned paper here, every separable Hilbert space has a totally ordered cone, and this theorem has quite large conclusion to equilibrium theory and finance. Oh, thank you very much for listening. Thank you.